To get some practice with our projectile motion equations, let's go ahead and solve a few basic example problems. So one basic example case we could look at is the case where you fire the projectile horizontally from some initial height and ask what is the range, what is the downfield range of the projectile in that case. So we just shoot our projectile and we see downrange at something like 21.3 meters. We fired it with an initial speed of 15 meters per second, as we can see here. So generally, when you go to a firing range like this, a basic piece of technology you can usually get is a tape measure. I'm going to assume we can get a hold of one of these. And one thing we could do is check, okay, they're saying we fire it from an initial height of 10 meters. We could just check that. And I'm measuring with my tape measure 10.03 meters. So that's pretty close. Looks like there's going to be, what's the error going to be on that? About 0.3%. It looks like there's about a 0.3% error to me on that one. Now as far as the downrange goes, I use my tape measure for that. So here I got 21.51 meters. This one says 21.3 meters. So one of those, up to some little bit of a measurement error, about 21.3 meters or so, is our range. So that's one thing we're going to want to verify if that's the case. Another thing we could do is just push this thing all the way down so it starts at an initial height of 0, and then go ahead and shoot that case. Say, okay, well, how far does it go in that case? It looks like in that case it goes about 17.5 meters. So those are two sample test problem cases we're going to want to verify. We're going to want to verify that the projectile motion equations yield the same results that we actually measure. That's pretty important, right? Your theory needs to be verifiable by what you can measure and show. So here's the questions. Here they're stated more formally. Find the horizontal range of a projectile fired horizontally, that means an angle of 0, with an initial speed of 15 meters per second from an initial height of 10 meters. So that's the default setting of the FET cannon. We fired that. We saw it was about 21.3 meters was the horizontal range. Okay. Now our job is going to be to verify that. And then the next one is going to be to find the range when we lowered the cannon all the way down to a height of 0, right onto the ground. And we saw that, what was the angle? That angle was 25 degrees. So here's a typo we can correct. Initial angle of 25 degrees. With the same speed, default speed of 15 meters per second. So with projectile motion problems like these, our go-to starting place is going to be our 2D kinematic description of projectile motion. And here's the equations, which we've derived right here, and here they're in our textbook. Here's our projectile motion equations. So we got the horizontal motion, vertical motion. This describes the vertical motion. What do they say the steps are? I have my way I like to do this. Let's see if it corresponds to what they say. So here's step 1. Resolve or break the motion into horizontal and vertical components. Shoot the motion independently in 2 dimensions. Solve for the unknowns. Alright. One thing we're definitely going to want to do is sketch the situation, then see if we can simplify our equations, and then go ahead and solve the problem. So the way I like to approach problems like this, projectile motion problems, is graph the situation, set up a graph coordinate system, and sketch the projectile motion out so I can kind of see what's going on. So we'll start with that. So we'll get our y-axis set up. Then we get our x-axis going. So our y-axis is the vertical axis. Our x-axis is the horizontal axis. Here in this case, our units are definitely meters. And now we're going to be shooting our projectile. Here in this case, we see it's got some initial height. We're firing it from some initial height. That initial height, I like to make that y0. So in this case, y0 is 10 meters. Y0 is 10 meters. Then it says, okay, we're going to fire it horizontally at an angle of 0. Okay, so that's definitely the case we're going to be going after. But let's just say, just for the sake of argument, just for a second, I didn't initially fire it from an angle of 0. Fired it at this initial velocity, say, okay, we'll call that v0. Say if that's the initial velocity. Then what would the projectile motion look like? Then projectile motion would look something like that, and it would land here. I'm going to call the range R. And then in that case, I would have x and y initial components of the velocity. And how could I find those? I'd have to break the initial velocity up into components. So if we fired it at some angle like that, then we'll have initial components of the velocity, x and y components. What will we have on this side? I'll have the initial component of the x velocity would be the speed times the cosine of the angle, and then the initial component of the y velocity will be the speed times the sine of the angle. Now when you fire the projectile horizontally, what happens in that case? Well, in that case, the angle will be 0. So you fire horizontally, then that's going to mean, well, in this particular case, theta is 0. And so what are we going to get? Then this would be the Vy0, the y component of velocity. Well, if the angle is 0, then sine of an angle of 0 is also 0. So this one would be 0. And cosine of a 0-degree angle is 1. So in that case, the x component of velocity will just be the initial speed. Alright, I'll show you how else we could look at this. Let's go back to the beginning and think about shooting our projectile. So if I shoot it like that, that's some angle, not 0. But what happens as we lower the angle? What happens as we bring it down towards the horizontal? The angle gets smaller and smaller and smaller, small, 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 until finally when you fire horizontally, now the angle is 0. So here's my initial speed, v0, or my initial vector, which has a speed 15 meters per second. And what can we say now? That's the initial velocity vector, and it only has an x component. You can see that. So we showed that before, that if I made theta equal to 0, I get the initial component of velocity in the y direction is equal to 0. Well, you can see that's the case here. There is no y component of the initial velocity. And the x component is just the initial speed. That is, all the initial velocity is fired in the x direction. So here's our initial velocity. It's Vy0 equals 0, and Vx0 equals the initial speed, v0. And then again, so we shoot it, and then our projectile will just start going. Again, our projectile lands at the range, or x equals r. And now the problem is for us to find that range, given the initial height and initial speed, which we shoot the projectile at. So here's our initial speed right here. They give us that. It's 15 meters per second. Okay, so how shall we approach this problem? Well, we've sketched the problem out, so that's the first step I like to do, sketch the problem out. Now you can see we've resolved the initial components of velocity. So our instructions here from our college physics textbook are step 1, break the motion into horizontal and vertical components. So we've kind of done that there. And then now we're going to be using our kinematic description of the motion. So here's our kinematic equations of the motion. Okay, so here's the x part, here's the y part. We don't actually need to use all these equations. Let's now apply what we know to simplify our equations. So the way I like to approach these problems is after I got my sketch down and I figure out what my initial velocity is, it's resolved into components. Then let's go ahead and simplify our equations of the motion as much as possible. Let's start off with the horizontal part of the motion. That's pretty simple. So the horizontal part of the motions, our equations, what do they tell us? They tell us that the velocity in the x direction is constant. It's just whatever you start off with. Right? It's just whatever the initial x component of velocity is, because there's no acceleration in the x direction. So the velocity in the x direction, the x component of velocity is constant. And in this case, it's just the v0, which we can see is our 15 meters per second. Now, the position versus time. The horizontal position versus time. The x position versus time equation. So that tells us that x is wherever it starts off at when you fire, x0, plus the x component of velocity times time. as usual, unless there's no good reason not to, and there usually isn't, I'm just going to set x0 equal to 0. That is, I'm just going to say, okay, wherever I fire my cannon from, that's where x equals 0. So that x0 is equal to 0. And then here in this case, the constant velocity in the x direction is just v0. So that's going to tell us that. Now, just using these simplifications, so that's my next step, is to use whatever I know from the initial conditions to simplify my equations. Use my initial conditions to simplify the equation. So that's my next step that I'm following here. I'm not numbering them 1, 2, 3, 4. The textbook has done that. But anyhow, you can see this is 0, and that's just going to be v0, so this is going to be v0t. So that's our x component stuff. Now let's do our y component. Let's simplify the y equations of our kinematic motion. So I'll just start with since I started with the x velocity, I'll look at the y velocity. So the y velocity is, okay, whatever it starts off at, the initial velocity in the y direction, and then minus gt. Tells us how the y velocity, or the y component of velocity, changes due to the action of gravity. That is, the y component of velocity is whatever it starts off at, its initial velocity, minus gt. It means that it's gaining velocity, but in the negative y direction as time goes on. It's turning, even if you shoot it up, that means it'll turn around and then start going down. And then the y position equation, that tells us that, okay, y is going to be wherever it is when you start the clock. Time 0 is when I shoot the projectile. That's when I start my stopwatch, if you will. And right as I start my stopwatch, y is at its initial position when it's at time 0. So that's the initial height here in this case. It's going to be 10 meters. Then plus vy0 times t, and then minus 1/2 gt squared. So that's our kinematic equations for constant acceleration. And here's the y component. Y position versus time equation. Here gravity is the constant acceleration, the only acceleration for our projectile motion, neglecting air resistance. Okay, now what can we do here with this? So we can simplify our equations a little bit. Our initial velocity in the y direction is equal to 0, so that'll just tell us, okay, vy is going to be whatever it starts off at, 0 minus gt. Okay, so vy0 is 0, so in this particular case, since the projectile is shot horizontally, it doesn't have any y velocity in the beginning, but it gets a y component of velocity as it flies through the air due to gravity, and that's what this is telling us. And then the y position, y0, that's not 0. We shoot it from some initial height, but there's no initial component of y velocity, so then this is just minus 1/2 gt squared. Okay, so now we've simplified both our horizontal and vertical component equations, or x and y equations for position and velocity. Now what do we do? So I've simplified my equations. First thing I did was sketch the motion, drew a graphical sketch showing the motion and highlighting what I'm interested in. Here in this case, I'm interested in the range, how far it goes. That is the horizontal range, which we're calling x equals r. Then, using my initial conditions, I simplified my equations of 2D kinematics as much as I could. Then now what do I do? What do I do next to solve the problem? Find the range. Okay, so what I do, and I do this for most projectile motion problems, is after I've done these first two things, is I just think of time now. I think of it now as the time of flight. I think of t now being the time of flight. That is, I think of the time as being the time when the projectile first touches down on the ground, because these equations are valid from the initial time t equals 0 all the way until the projectile touches down, smacks down on the ground. Then after that, these equations no longer describe the motion, because then at that time, what would the displacement of the object be? Okay, well, I'll use s for displacement. For all times after that time, t is the time of flight when it smacks down. For all times after, what is going to be the position of our object? It's going to have an x position equal to the range. It'll just sit there where it smacked down, and its height will be 0 because it touched down on the ground. So that'll be the x and y position. X position will be the range, the y position will be 0. So, and I'm just now going to use that. So when t is equal to the time of flight, then x will be equal to the range, and that's going to be v0t. But now t is the time of flight. And here y, what is y going to be? Y is going to be 0, and that is equal to y0 minus 1/2 gt squared. Okay, so now what can I do? Well, they're asking me what is the range. It's this r guy right here. So r is v0t. Well, I know the v0, that's 15 meters per second. And the t, well, that t is equal to the time of flight. That's my assumption here. But I don't actually have a number for what the t is. But let's see, can I get a number? Okay, let's look over here. When t is equal to the time of flight, and that's what this t is, that's the time of flight, then all this stuff is equal to 0. So I could actually solve all this for the t. In fact, the first step would be move this term to the left-hand side of this equation. This minus term, this minus 1/2 gt squared. 1/2 gt squared is equal to y0. That's coming from this equation right here. So now I can solve for this t right here. This t, what's that equal to? Just solve for it. 2y0 divided by g, take the square root. So this tells me what my range is. So now going over here, I'm just going to substitute this t in for this t over here. That's the time of flight. The range we're looking for is the initial speed times 2y0 over g square root. Now, this is becoming a job for our calculator. So now I'll just put in my numbers. So the range is v0, so it's 15 meters per second, times the square root of 2 times the initial height divided by 9.8. G is 9.8 meters per second squared, square root. Alright, so now we'll work that out with our calculator. And I got 21.4 meters. Now let's check our units here. So how are units going to go here? I'm going to have meters canceling with meters. This meters will cancel with this meters. Then what do I have here? I have 1 over second squared. And that's all under the radical. But 1 over second squared is going to be a downstairs goes upstairs. So that's going to overall be equal to second squared. 1 over something is just the something. So 1 over second squared is just second squared. So it's second squared, but square root. So you take the square root of second squared, that's just seconds. And so that means that this seconds is going to cancel with, well, this is going to all turn out to be seconds. So I'll just go ahead and cancel here. This whole thing will turn into second squared, square root is seconds. So that seconds will cancel with this seconds. And all I'm left with is meters. And then our final answer is going to be range equals 21.4 meters. And as we can recall back from our PhET sim, using the tape measures and the bullseye there with the meter gauge on it, we saw that the range was somewhere between 21.3 and 21.5. So there it is right there. There's our answer, 21.4 meters. I'm quite confident it's correct. So now we've solved problem A. Now we're ready to do part B. Find the horizontal range in the case where we fire the projectile right off the ground at an angle of 25 degrees. Again, here's the same initial speed. Okay, so now we're firing our projectile right off the ground, and I know the angle's small, something like 25 degrees, but I'm going to exaggerate the angle like that just to make it easier for me to write my angle down on there. And that's going to be our initial velocity that we shoot it off at. And it is a vector, so I'll go ahead and put this little arrow over it. That means it's a vector. Then we shoot our projectile. So I'm going to sketch what happens on here. It goes like that, and then touches down here at x equal to the range. And again, that's what we're looking for, what that range is. So as before, I'll start off by resolving my initial velocity into components. So the initial velocity vector has x and y components. Projectile shot at an angle above the horizontal, and here that angle is 25 degrees, or we can see that's what theta is. Theta is equal to 25 degrees. So again, using our basic trig, we know that the speed forms the hypotenuse of the right triangle for the vector, for the velocity vector. So this v0, 15 meters per second, that's the hypotenuse forming the right triangle of our initial velocity vector. So the x component is given by the side adjacent of the triangle, the right triangle forming the velocity vector. Therefore, Vx0 is the speed times the cosine of the angle. So that's the initial x component of velocity. The initial y component is the speed times the sine of the angle. And that's just from our basic trig, our basic rules for trig. SOHCAHTOA. If you're not familiar with those rules, then, or you've gotten rusty on it, you could just go back and look at your trigonometry book. Alright, so I've resolved my initial velocity vector into its x and y components. As before, I'll go back and try to simplify the projectile motion equations. We'll start with the horizontal component equation, x component equations. So Vx, that again is just whatever the initial component of velocity is in the x direction. Here, and in this case, we know there is some angle, it's 25 degrees, so it's going to be v0 cosine theta. And then now x, our x position, that's going to be whatever it starts off at. And again, I'm just going to take x0 to be equal to 0 plus the x velocity times time. And in this particular case, I know that x0 is equal to 0, so this is just going to be vx0 t. Because what I'm saying is x0 is equal to 0. As before, we just assume that we shoot them from the location where x is equal to 0. That is, we put the origin of our axis right where we shoot the projectile from. Now let's go to our vertical component, our y component of the motion. So our y velocity is given by vy0 minus gt, so that's what we get for that. And then our y position is given by y0 plus vy0 t minus 1/2 gt squared. And x0 is equal to 0, also y0 is equal to 0. We're firing it from an initial height of 0. So for our simplification, what will we get? Okay, this is v0 sine of the angle minus gt. Doesn't really simplify that one too much in this case, but this one, what do I get here? I get the y0 is equal to 0. So this term simplifies, so this is just becomes 0t minus 1/2 gt squared. So these are our reduced equations then. That's my reduced horizontal motion equation, and here's my reduced vertical motion position equation. Reduced horizontal motion position equation, reduced vertical motion position equation. Okay, so again we're looking for the range. So I sketched a situation, I reduced my equations as much as the initial conditions would allow me to, substituted in my initial conditions to see if I could get any reduction. So by setting x0 equal to 0, we reduced that one down a little bit. And then since the initial height is 0, I could reduce this one down a little bit, get rid of that term. So now, again, I'm going to do the same trick as I did last time, or the same technique. Now what I do is I think of t being the time of flight. Let the t equal time of flight. Here, I'll just abbreviate it. So when t is equal to the time of flight, again, the position is going to be x equals a range. The horizontal position is x equal to range, and y is equal to 0. So I could write my position vector s, do it the same way as I did before. So my position vector s, just generally position vector anywhere along the curve, let's say here at this spot, that's the position vector s. When it gets to this spot, then what is x going to, so at any place along the trajectory, the position vector is just specified by the x and y position. But right down here, when t is equal to the time of flight, what is that? When t is equal to the time of flight, then the x position is the range. That's where it touches down. By definition, that's the range. And y will be equal to 0, because it lands on the ground. Define the ground to be where y is equal to 0. Okay, so we have that again for this problem. That's a pretty typical setup. So we're thinking of t is equal to the time of flight. So when t is equal to the time of flight, x is equal to the range, and that's equal to vx0. And vx0, what is it? I'll just go ahead and put it in terms of the cosine of the angle. v0 cosine of the angle. And that's all times the time t, which right now we don't know. We know the angle, so we can find the cosine of the angle because we know the angle. We know the initial speed, v0, that's 15 meters per second. So if I knew what the time was, the time of flight, then I would solve the problem, right? Then I would just put that time in, and I would calculate the range with it, since I know the speed and the cosine of the angle. Okay, but I don't know the time yet. So how am I going to get the time? Well, I can see I'm going to be able to get it from this equation, because look what happens. At t is equal to the time of flight, y is equal to 0. then that's going to be equal to Vy0 t minus 1/2 gt squared. All that's equal to 0. So this is going to allow me to solve for the time from this equation. One thing I can do is divide both sides of this equation through by t. So 0 divided by t is still going to be 0, but then if I divide this side by t, I have to do the same thing to the other side of the equation. And so I divide this right-hand side of the equation by t, and if I do that, I have to divide both of these terms by t, so that'll knock out this term, and then t squared will just become t. One of those t's will cancel. So I can cancel off 1 power of t in each term, and then now I can solve for the t. So t will be 2 Vy0 divided by g. And then now I can put that value up over here in this equation. So that means that substituting this value of t into this range equation, I'm going to get the range is equal to, so this is going to be 2, since Vy0 is V0 sine of the angle, that's all divided by g. Now I can substitute this value of t, which everything here is known. I know what g is, it's 9.8. I know what the angle is, so I know the sine of the angle. I know V0, so now the time is completely known. It's completely written in terms of knowns. So let's substitute that in over here. And by the way, we could solve this numerically if we wanted. Put in our values for everything, calculate what this time of flight is, and then go up and put that time as a number into this equation and put our numbers in for these things and get the range. But I'm going to do it just a little more generally. So I'm going to write the range now like this. The range, by substituting this in over here, I'm going to see it's equal to, okay, 2 E0 squared times sine of the angle times the cosine of the angle, all divided by g. So all I did was I substituted this value in for t over here, rearranged terms a little bit. Check my algebra out on that for me if you want. I did it kind of all in one step just to save space because I'm running out of room here. And I happen to know that there's a trig identity I can use here to simplify this formula just a little bit more. Trig identity is that 2 times sine of an angle cosine of an angle is sine of twice the angle. So that's going to reduce this a little more for me. It's going to become E0 squared times sine of twice the angle, all divided by g. And if we look over at our equations of projectile motion from our college physics textbook, we can see that the equation we just found for the range corresponds to this range equation for the case when you fire a projectile from the ground. So what is the range? When you fire a projectile from the ground at some angle and then it hits the ground. So it fires from and touches down at the same level horizontally. It's fired on horizontal ground at an angle, then this gives us the range. And that's exactly what we just found solving our problem. So essentially we just derived the range equation. So now we're just going to go ahead and put in our numbers then. So for the case we're considering, our range is going to be just using this range formula we just derived and our numbers here which we have. So initial speed 15 meters per second squared, we got to square it, V0 squared times the sine of twice our angle. So our angle here, our initial angle is 25, twice that's going to be 50. 2 times 25 is 50 degrees. And then we got to divide all that by 9.8 meters per second squared. You can see what are our units going to be. So I have per second squared in the denominator over here, and in the numerator I have also a per second squared. I'm going to actually have meter squared over second squared. So that per second squared will cancel with that per second squared. And then I'm going to have meters in the denominator and meters squared in the numerator. So that one's going to cancel, and it's just going to leave meters up top. So I'm just going to end up with my answer in meters. The unit of length, which as we should, we must have the answer in meters since everything here is in SI units, and range has to be a length. So that all looks good. So let's go ahead and put in our numbers to calculate this. So rounded, I got my range is equal to 17.6 meters. We can just go look at our FET cannon real quick and double check ourselves that that indeed was the range we measured for this case. Looking over here back here at our FET cannon, And just fire again. And see, indeed, 17.6 meters is definitely the range. We're measuring it directly right out here at our FET projectile motion firing range.